All right, good morning, chemists. Let's get started. Are there any cool outfits today? Any cool outfits? I got all this prepared for you guys. We'll wait for the demo until the end of class. So we have something to look forward to, but it's business as usual here. We're just going to continue on with Chapter 9. All right, so hopefully you can pay attention. All right, so a couple of announcements before we get started, though. I was looking at the lab schedule, and it seems that most of you who have like lab on Wednesday, Friday, and Monday, oh wait, we have a costume right here. Yes. Your gas lab is the very last in-person lab that you're going to have for Chemistry 1210. And then, yes, some clapping. And your last lab will be MGB, which is molecular geometry, which covers the topics in Chapter 9. But that is a digital lab that you'll do a little bit later. So I just wanted to give some tips about this gas lab, because this is a really great lab to do in person in the space, but unfortunately we have not covered gases yet. That's actually Chapter 10, so I just wanted to give some tips here for when you do that gas lab. In that lab, you're going to make this weird apparatus to collect gases from some type of chemical reaction. They talk about percent recovery, and because the apparatus isn't very good, you're not going to be collecting 100% of the gas that you produce in that reaction. So you can really just think of percent recovery as percent yield, where, percent yield is your actual yield over your theoretical. So just think of percent recovery as percent yield. Where theoretical, this comes from stoichiometry. Like, you'll know how much theoretical yield of gas you make from the balanced chemical reaction. Moles make moles in doing stoichiometry, but your actual is what you actually, measure in lab. So just think of it as percent yield, all right? Like, if your apparatus is only 50% recovery, then that means based upon how much you actually measure in lab relates to the theoretical that you would have calculated from stoichiometry. So just think of percent yield in that case. I've already posted Chapter 10 slides, so if you want to look at those slides to help you in that lab, go ahead and do that. But basically, you're only going to be using one equation, PV equals nRT, where R is the gas law constant, and it has this unit, liter, ATM, mole, Kelvin. And so based upon the unit, you can tell what the units of all of these variables need to be. Pressure needs to be in atmospheres, volume needs to be in liters, N is moles, and T is your temperature of your sample in Kelvin. And so that's basically the only calculation, that the equation that you need to do. And R, that gas law constant, tells you the units of all of these variables in order for that equation to work. All right, so that's just some tips on the gas law lab. So now we'll just move on to Chapter 9, where we talk about molecular geometry. Hopefully you spent over this weekend not only doing Chapter 7 homework, but also going over the 6 steps for Lewis structures, because we're going to continue on doing that. But now we're going to be using those Lewis structures that we made from Chapter 8 and utilize VSEPR theory to predict the shapes and those bond angles for molecules and how they actually look like in real life. So first we'll be talking about molecular shapes. The big idea here is what we draw in the Lewis structure doesn't necessarily show what that molecule looks like in 3 dimensions, in real life. Electrons are not dots on a page. So when we draw a molecule flat with its Lewis structure, it doesn't mean that molecule is flat. We need to think about electrons existing in 3 dimensions. And then Chapter 8, we talked about basics of bonding, ionic and covalent bonding. In this chapter, the second half, we will talk about advanced theories of bonding. So we will be learning something advanced, all right? Okay, so what do molecules look like? So the big idea is electrons are not dots on a page. Hi, Jerry. So here we have a carbon atom attached to 4 different things, 4 different bonds. So even though we draw this molecule, we go through like the 6 Lewis structure steps, we get that carbon here, it looks flat. It has 4 different bonds, 4 different chlorine atoms to it, but when we draw it flat, it implies that there's a 90-degree angle between all of those bonds, but that's not necessarily the case. Because we drew this molecule on paper, it looks like it's flat, but it's not. And so molecular shape is really important in terms of predicting chemical reactivity, physical properties, so all of this is going to come together for us to understand how molecules behave. And so here are some different examples of molecular shapes and kind of some interesting things. So here we have a molecule where A is our central atom and it's attached to 2 other things, these 2 B atoms, but we can have a different, multitude of shapes. Here, this molecule, those 2 B atoms are 180 degrees from one another. It's linear, but in this molecule, it's bent. Those 2 bonds are bent. So how does that happen? It all has to do with the Lewis structure. So both of these molecules exist, where one's linear and the other is bent. Or in this example, our central atom is attached to 3 different things, and we have 3 different molecular shapes, but with that same connectivity. Here we have a trigonal planar molecule, this is trigonal pyramidal, and here we have a T-shaped molecule. So based upon the number of bonds, we can have different shapes, and we'll talk about how we can predict what shapes our molecules adopt. And it's a very systematic thing, just like Lewis structures. All right, okay, so how do we determine the shape of a molecule? So the thing you gotta get in your head is that bonds, they're made of electrons. Lone pairs, they're also made out of electrons. Electrons are what charge? Negative. And so if bonds are made of electrons and they're negative, lone pairs are also negative. Electrons always repel one another. So based upon the number of electron domains around a central atom dictates what shape it adopts, where we both have to consider electrons that exist in bonds because they're made of electrons, and also electrons in lone pairs because they are also electrons and they repel one another. So the first step to determining a molecular shape is to predict or count the number of electron domains around that central atom. So we want to consider the electrons that are in bonds and the electrons in lone pairs, and then that will give us our template for what our molecule actually looks like. And here are those shapes down here. But the thing is when we look at molecules, we're not actually looking at the lone pairs. We're only really looking at the chemical bonds that are present, but we do see the influence of lone pairs if they are present. And so that gives us the idea of molecular domain. The molecular domain geometry just looks at the electrons that are in lone pairs. And I'll show you some examples of that. So when I ask you what is the molecular geometry of this molecule, what I'm asking is where are those bonds actually located around our molecule, but also consider where are those lone pairs present. Okay, is Jerry going to be okay in class? Okay, he's okay? All right, so here are our electron geometries. So remember, depending on how many electron domains, so again, remember to consider both bonds and lone pairs, we get these different shapes. I like to call these parent shapes where, again, electrons, they repel one another. They want to get as far away from one another as possible, and we get these different shapes. We have a linear arrangement of electron domains, trigonal planar, we have a tetrahedral molecule, trigonal pyramid, and an octahedron molecule. And so the idea here is just depending on the number of electron domains, those electron domains are going to spread out as much as possible to give each other as much room as possible. Where's my linear molecule? This one's not linear. That's okay. All right. So in this molecule, all right, we have our central molecule, and there's 3 different electron domains around it. So if you just think of electron domains as like if you have like a brother or a sister, and like Siblings, they never get along, and they always want to get as far away from one another as possible. That's the big idea here, is that these electrons, they want to orient themselves so they have as much space as possible. So in a molecule where there's 3 electron domains, each domain will give itself 120 degrees, so it's far away as possible from one another. I guess 3 is kind of easy to see, where you see there's 120 degrees, and that's as far away as it can get. But once we get a little bit more complex, like a 4 electron domains, we're no longer in this like planar arrangement. In order for these 4 electron domains to give one another as much room as possible, we actually want to make a tetrahedron, where each of these bond angles are actually 109.5 degrees away from one another. So we have this 3-dimensional shape instead, but you see that each electron domain has as much space as possible. They're like 4 siblings who hate each other, and they want to give each other as much room as possible. That's 4 electron domains. 5 electron domains is a trigonal bipyramid where there's 2 regions. There's like these 2 that are 180 degrees from one another, but then the last 3 electron domains are 120 degrees from one another. You can see it like that. But then we have 2 on the top and bottom here. And then finally, 6 electron domains makes an octahedron where each bond angle is 90 degrees from one another, and then the top and bottom here are 180 degrees from one another. So the interesting thing, with using Vesper theory, the idea that electrons repel one another, even though we draw methane with 4 hydrogens and the molecule looks flat, the molecule is actually not flat. It exists in 3 dimensions with 4 electron domains in a tetrahedron shape, 109.5 degrees away from one another, even though we draw it flat, right? So absolutely memorize these electron geometries, all right, and their bond angles, all right? So this is electron domains, where we're not really distinguishing between bonds and lone pairs. So where we get our molecular geometries is now we just need to consider where are those lone pairs at. So the idea here is you always start with your electron geometry, like on this page. Then you want to think about, we can't see lone pairs, we only see bonds. So what we do is we take our electron geometry, what I call the parent structure, and we just cover up certain areas that lone pairs exist, because we can only see bonds, we do not see lone pairs. So we use our electron geometry as a template. So this chart shows you, okay, these are all of our parent geometries, linear, trigonal, planar, tetrahedral, etc. So all of these molecules, all of their electron domains are bonds. So this is 0 lone pairs. All of those electron domains are bonds. But once we start adding lone pairs to our structure, so let's say we have a trigonal planar electron geometry, but one of those, one of those domains is a lone pair, what we do is we just make one of those domains a lone pair, and we put it like that, and the idea here is that we only see bonds, we don't see lone pairs. So in order to say what the molecular geometry is, all we do is cover up that lone pair and we ask ourselves what shape is left. What shape is left when we put one lone pair on this trigonal planar? What does that look like? It looks bent, doesn't it? And so that's the shape that's made when there's one lone pair present. If we go down to a tetrahedral, same idea. If we have a domain, electron domain of 4, but one of them is a lone pair, we just place that lone pair somewhere. We squint our eyes and pretend that we can't see that lone pair, and we say what shape is left over. And so in this case, it is a trigonal pyramid, where it's just kind of the 3 feet of a pyramid, but not the top part. If this tetrahedral has 2 lone pairs on it, then we put those 2 lone pairs on. But if we want to say what the molecular geometry is, we just cover up those 2 lone pairs and we ask ourselves what shape is left over, and that would be bent. And that's what we see in these boxes where, okay, we put 1 lone pair on the parent structure, we put 2 lone pairs on the structure. We just say what shape is left over once we use that electron domain as a template. So a common thing that students will say is, for example, if we had, something with 2 bonds, and 1 lone pair. How many electron domains is that? How many electron domains? We just counted them up. 3. All right, so because remember, electrons exist in bonds and lone pairs. So this molecule, if it has 2 bonds and 1 lone pair on the central atom, so like 2 bonds and a lone pair, this has an electron domain of 3. So that means its electron geometry is trigonal planar. But oftentimes we'll ask, okay, what is the molecular geometry of this? And a lot of students will say, oh, it's linear because it only has 2 bonds. But you're neglecting the presence of that lone pair there. And so what we actually say is, okay, if it has an electron geometry of 3, one of those domains is a lone pair, and so the shape is actually, okay, what if we just don't see that lone pair there? This molecule is actually bent, not linear. So that's oftentimes the mistake there. Students will say, oh, the electron geometry is trigonal planar, the molecular geometry is linear. Those two shapes don't superimpose on each other. So our electron geometry is always the template for our molecular geometry, all right? And so these are all the different shapes, and they have names that are similar to that of what it looks like. And we'll go into detail there. All right, so here are the steps, the systematic steps for determining the geometry of a molecule. The first step is actually 6 steps, and that is draw the molecule using the 6 steps for Lewis structure. So if I give you like a molecule like CF4 or something, you have to actually draw the Lewis structure first, especially if I don't actually give it to you, right? So once you have that Lewis structure, now you just want to inspect the central atom, all right? So we usually use Vesper theory on the central atom. And so around that central atom, you want to count how many electron domains you have, depending on how many bonds and how many lone pairs are directly attached to that central atom. All right? And so from that electron domain number, you can get your electron geometry, and that is your template. And then the last step is, okay, now consider where are the lone pairs. So put those lone pairs on your electron geometry template, then cover up those lone pairs and ask yourself what shape is left over. That is your molecular geometry, all right? Okay, so you take account of lone pairs. All right, so let's practice, all right? And so in the next slide, I'll give you a second to write all of this down. But all of it stems from, do you have the correct Lewis structure? That's the first step. So in the next slides, I'm going to just give you the Lewis structures, and we'll take it from there. All right. So good. We good? Okay. All right. Okay. So let's do these. All right. And of course, refer to those 2 slides with the molecular shapes, because we'll need those once we get the numbers. All right, so I have the different molecules. I already did the 6 steps for you, and here are those Lewis structures. So let's do ammonia first. So this is NH3. So our strategy here, since we already have the Lewis structure, is all we want to do is inspect that central atom. And so I see on that central atom how many bonds are on it and how many lone pairs are on it. How many bonds? 3. And then how many lone pairs? 1. And so all of those, all the bonds, all the lone pairs add up to the electron domain. And so this molecule has an electron domain value of 4. All right? So we ask ourselves, okay, 4 electron domains, they spread out as much as possible to give each other as much room as possible. So what shape is made when 4 electron domains spread out? What is that called? Tetrahedral, yes. So we have a tetrahedral, and it's abbreviated TD. All right, so our molecule, its electron domain geometry looks like this, where there's 4 domains spread out equally, all right? But our molecule does not look like a tetrahedron because there's 1 lone pair present, and we have to consider that. We have to think about, okay, we can't actually see that lone pair, but we do see its influence. So the idea here is, okay, we have a tetrahedron, so I'm gonna draw it. So we got a tetrahedron, it looks like this. All right, so that wedge and dash, I'm just trying to make it look 3-dimensional. Doesn't it look 3-dimensional here? All right, so those are our 4 electron domains, but we need to think, okay, one of those domains is actually a lone pair, so I'm gonna draw it right there. It doesn't really matter where I draw it because all 4 places are the same, so I could put it on the side as well. All right, and so our molecular geometry is when we look at this structure, but we ignore the lone pairs, what shape is left over. So what I often like to do is literally erase it. When you erase it and you ask yourself, okay, what shape is left over, what does that look like? It's trigonal pyramidal. It's not trigonal planar, all right? It's trigonal pyramidal where those pieces where we don't see the lone pair, those 3 bonds are actually kind of splayed out to make a pyramid shape. So our molecular geometry here is trigonal pyramidal. All right, it's not trigonal planar. All right, so there is ammonia. All right, so let's do CH4. Okay, what's the electron domain number? How many electron domains do we have? 4, yes. And so of those 4, all 4 are bonds, and we have 0 lone pairs. So what is the electron domain? It is tetrahedral again. All right, so I'll go ahead and draw it. So here's my tetrahedron, so wedge and a dash. All right, do we have any lone pairs to worry about? Nope. So then what is our molecular geometry? It is the same shape because I don't have any lone pairs to consider. So our molecular geometry is also tetrahedron. All right, so anything that has 0 lone pairs will always adopt one of the parent structures. So like linear, trigonal planar, tetrahedral, trigonal bipyramid, or octahedral, if it has 0 lone pairs. All right. Okay, so let's do this next one. So this one's a little bit different because there's a double bond present. So this work that we did to calculate the electron domain number, I had it in a slide, but I kind of glossed over it. When we're counting the number of bonding domains, a single bond is the same as a double bond is the same as a triple bond. So each of those only counts as 1 bonding domain. And the reason is, in a double bond, how many electrons are involved in a double bond? 4, yes. But those 4 electrons, they're all together. They're all in one small space, so they're going to move together. So in this molecule, there's 2 bonding domains and there's 1 lone pair domain. So basically there's 2 bonding domains, So I'll just highlight those. It's this domain and that domain. They're moving together. That double bond, it doesn't split up or anything. We're going to treat that as 1 bonding domain, regardless if it's a double bond, a single bond, or a triple bond. And then there's also 1 lone pair I have to account for, so I'll highlight that there. All right, so how many, what's the electron domain number here? It would be 3. Yes, it is not 4. Okay, so if you said 4, in my mind, I would think, oh, you treated that double bond as 2 bonding domains. No, all 4 of those electrons move together, so it just counts as 1 bonding domain. So this is an electron domain number of 3. So what shape is that? Trigonal planar, yes. All right, so I'll just draw what that looks like. All right, trigonal planar is everything's 180 degrees from one another. All right. So that is our electron domain geometry. Do we have any lone pairs to consider to get to our molecular? Yes, there is. There's 1 lone pair. So we need to consider that 1 lone pair. So I'll just put it right here. Doesn't really matter. All right. And then to get our molecular geometry, we literally just erase that lone pair and ask ourselves what's left over. So what's left over? It's bent, yes. So our molecular geometry will be bent once we utilize and recognize where that lone pair is and that we can't see it. All right, so our molecular geometry is bent. All right, last one here, SF4. All right, so even in this Lewis structure, I'm trying to communicate to you what it looks like, but let's get it ourselves. What's the electron domain number here? 5. So 1, 2, 3, 4, 5. All right. And so 5 electron domains is what shape? It is. If you look back at that slide, it's trigonal bipyramid, right? And so what that shape looks like is we have this like north and south arrangement going on like that. We have 1 bond going out like that, 1 coming out of the page and 1 going into the page. So you see that there are 5 electron domains spread out as much as possible. But do I have a lone pair to consider? This is just our electron domain geometry. That's where all of our electrons live, but we have one lone pair to consider, right? And so that one lone pair to consider, we actually want to put that lone pair in a place where it has the most space, and I'll talk about this in a little bit, but that lone pair is actually going into the equatorial position, so kind of like the belt region of this trigonal bipyramid. And the reason is because lone pairs are kind of diffuse and puffy, and so they want to go into a place that has the most available space for them, and so that's going to be in this position where the other closest bonds are 120 degrees away from it. We don't want to put the lone pair up top here, all right, because if we put the lone pair up top, then this lone pair is 90 degrees from other bonds, and we don't want that. That's not as much room as possible for a lone pair. So we actually want to put that lone pair on the side here. I actually don't want to put it there. I'm going to put it here instead, but it's still the same spot. I'm going to put the lone pair here instead. All right, and so then to get the molecular geometry, we literally just ignore that lone pair and ask ourselves what shape is left over. What does that look like? It's a seesaw, but it's like on its side, or it's kind of like, yeah, on the tip. If you kind of move the molecule over, you can see that these two legs are kind of the middle of the seesaw, and so our shape is left over would be seesaw. All right, so those are the steps. We have to start with a correct Lewis structure. First, consider the electron domain geometry, where we count all bonding domains and lone pairs, and then the last step is to get the molecular geometry, where we actually place those lone pairs on the molecule and ask ourselves what's left over. All right? Okay, so, oh crap, we have more. Dang, hot dang. Okay, all right, so let's keep going. Let's go a little faster now. All right, water, how many electron domains? 4. And so what shape is that? Tetrahedral. And so when we draw our tetrahedron, 1, 2, 3, 4, how many lone pairs are we going to place? 2. And so that means we're going to cover up how many of those like legs, how many of those domains are we going to cover up? We're going to cover up 2. So just cover up any 2. So I'm going to cover up that one and that one. And so we see once we consider those 2 lone pairs, what shape is left? Bent. Yes. It is not linear. Water is not linear. Water is bent. All right. Nitrate. How many electron domains? 3, yes, because the single bonds count as 1 each, and the double bond also counts as 1, because that double bond, those 4 electrons are all moving together. So this molecule has 3 electron domains, where there's 3 bonding domains and 0 lone pairs. So what shape is that? Trigonal planar. What about the molecular geometry? Is also going to be trigonal planar, because there are no lone pairs to consider there. All right. Okay. Good? Is that one good? Yeah, no lone pairs. All right, BF3. So the Lewis structure makes it look like it's T-shaped, but do you think BF3 is T-shaped? It's probably not. So let's use Vesper theory and check for ourselves. So how many electron domains? 3. Are there any lone pairs to consider? Nope, so there's 0 lone pairs. So that means its electron geometry will be the same as its molecular geometry. And so that would also be trigonal planar here. So both the electron and the molecular geometry are both trigonal planar, because there are 0 lone pairs. 3 electron domains spreading out as much as possible. All right, SF6. What's the electron domain number? 6. Yep, there are 6 bonds. 1, 2, 3, 4, 5, 6. And so if those 6 bonds spread out as much as possible, it's going to make an octahedron. And since there are 0 lone pairs present, our molecular geometry will also be octahedron. All right. So that's how we navigate. That's how we navigate using those tables. We just want to consider where are our bonds, where are our lone pairs, and how do those fit together in terms of electron and molecular geometries. All right? Okay. So there are electron shapes. All right, our molecule shapes. So let's just look into some small details of deviations from those electron shapes. So actually, before we do that, If we want to talk about an octahedron, let's talk about those ideal bond angles first. All right, so here's our octahedron. Let me try to make it three-dimensional for you so it kind of looks more like what it would look like, where those two wedges are coming out of the board and those two dashes are going into the board. What are our ideal bond angles on an octahedron? So like the bond angle right there, what do you think? It's gonna be 90 degrees, all right? Same thing right here, that's gonna be 90 degrees if it exists in 3 dimensions. So here's our octahedron. You can check for yourself. This bond angle is 90, these bond angles, everything's 90 degrees from one another, all right? What about in our BF3 example? What are our bond angles there? So remember what shape we said it is? It's trigonal planar. So does this Lewis structure represent what this actually looks like? No, it's not, because the ideal bond angles aren't 90 degrees like this. Trigonal planar actually looks like this. So our bond angles in BF3, what's that bond angle? 120 degrees, yep. And same thing with nitrate. What's our bond angle there? 120 degrees, yes, because both of them have that same shape, trigonal planar. What about water? This OH or HOH bond angle, is it 180 degrees? No, it's not. So if we look back at our molecular geometry, this bond angle, which remember came from our original tetrahedron, what are the bond angles on a tetrahedron? 109.5. So this bond angle is going to be about 109.5, right? That's just using the ideal bond angles that come from that chart a little bit up here, right? Up here, we have those bond angles. The ideal ones are right there, 90 degrees, 180, whatever, right? But I'm here to tell you that those are just ideal bond angles. Okay, there's also some deviations from ideal bond angles. We need to consider the influence of lone pairs, all right? So the idea here is that, you know, when we consider electron domains, electrons can live in bonds or in lone pairs, either. But I like to just think that when electrons live in lone pairs, they're just like big, fat, and juicy, and they take up more room than a bond. Right? So when you have lone pairs present on a molecule, it's going to push bonds a little bit closer together. So here's an example. So here's CH4. So this has an electron domain of 4. Same thing with NH3 and water. All of these have an electron domain of 4, so they all have a tetrahedron as their template. But the difference here in ammonia, there's one lone pair. In water, there's 2 lone pairs. So if we look at the bond angles as we go from molecule to molecule, we see that even though all of them start with an electron domain shape of a tetrahedron, we see that in water, the bond angles are just a little bit closer together. And the big idea is just these lone pairs are just big, fat, and juicy, and they take up a lot of room. And they push the bonds a little bit closer together to deviate it a little bit away from that ideal bond angle. Versus CH4, there's no lone pairs, all right? Everything's kind of symmetric in that case. And so we see that all the bond angles are identical. They're all 109.5. But once we start adding lone pairs, we get a little bit of deviation there. So yeah, the big idea here is that a lone pair is larger than a bond. And if you have lone pairs present, it's just going to push the other bonds closer together because that lone pair is big, fat, and juicy. That's how I like to think of it. Right? We also see deviations from those ideal bond angles with multiple bonds. So let's just look at this molecule real quick. All right? So let's look at that central carbon atom. How many electron domains are around that carbon? 3. 3 electron domains. So what shape is that? Trigonal, which one? Planar, okay. And so what is the ideal bond angle in a trigonal planar? So 1, 2, 3. The ideal is 120 degrees, all right. But since we're talking about deviations from ideal bond angles, do you think that indicated bond angle, do you think that's 120 degrees? No, it's not. And so it's the same idea of comparing a bond and a lone pair. A lone pair just takes up more room. So let's think about it. What do you think takes up more space? A single bond or a double bond? Which one takes up more space? A double bond, yeah, because a double bond contains how many electrons? 4 electrons versus a single bond is only 2 electrons. So in this case too, this lone pair, or sorry, not the lone pair, this double bond just takes up more room than our single bonds, so this whole molecule just kind of comes in on itself. And those bond angles get a little bit closer together. So this indicated bond angle right there, what do we think that bond angle will be? Will it be exactly 120? No, it won't. Which one is it going to be? Less than, yes, it's less than, okay? But what if I asked you, what is this bond angle right here, the red one? If I asked you what that red bond angle will be, what will that be? It'll be a little bit more than 120 degrees because it's part of that big cloud where those 4 electrons in the double bond reside. Right, so here the red bond angle is slightly more than 120 degrees, but this inner one is slightly less than 120 degrees. Right, so do be sure you're noticing which bond is being indicated and where deviations can occur. Deviations can occur in 2 places, if lone pairs are present or if double bonds are present. Okay, all right, okay. Let's revisit resonance from chapter 8. Okay, so we're still talking about deviations from bond angles. All right, so look at this example. This is nitrate. So remember we talked about nitrate, right? And we can calculate the bond order for the NO bonds in this molecule. Does this molecule have 2 long bonds and 1 short bond? No, it has 3 bonds that are all the same length because we can drill 3 different resonance structures. That double bond smears itself around the entire molecule. So with that in mind, what do you think the bond angles are in nitrate? Do we think we're going to have bond angles where 2 are bigger and 1 are smaller, or are all of them going to be the same bond angle? What do we think? So take a second, think about it, and talk to someone next to you what you think it's going to be. A, all of them are the same bond angle, or are we going to have 2 big bond angles and 1 small bond angle because of that double bond? What do we think? Okay. All right, who thinks A? All of them are the same bond angle. And then who thinks B? All right. Okay, so the correct answer is A. They are all the same angle. Yes. So I know, but we were just talking about deviations from bond angles and double bonds. They're big, fat, and juicy. But remember, does that double bond live here? No, that double bond is smeared around the whole molecule. So this molecule does not have 1 double bond and 2 single bonds. It actually has 3 bonds that are actually all what bond order? What did we calculated it last chapter? So it's 4 bonds around 3 different positions, so the bond order here is 1.33. So we have 3 bonds that are actually all identical, 1.33. So our correct answer is actually they are all exactly 120 degrees from one another because all of them have the same exact bond angle or bond order. Even though I draw this molecule with 1 double bond, we have to consider resonance. Resonance affects bond length, bond order, bond strength, and bond angles. That double bond doesn't live in one place. It's actually smeared across that entire molecule. All right, so our bond angles are all exactly 120 degrees. If this was a molecule that, if this was like formaldehyde or something like this molecule does not undergo resonance. So in this example, yes, that double bond does take up more room and we'll have bond angles of like about 125 and 110. But in this example, because that double bond exists in 3 different places, they're all exactly the same. So in this one, there are deviations from ideal bond angles, but in nitrate, there is not. And that's because of the idea of resonance taking place here. So I tricked you a little bit, or I tricked half of you. Yes. Okay. So let's practice this. all right? Let's estimate these bond angles. Okay, just because I draw this molecule like flat and straight doesn't mean all of these bond angles are 180 degrees. That's not necessarily. We have to think about, okay, what is the electron geometry? Are there any double bonds or lone pairs that we need to consider? So my strategy here is let's look at each of these central atoms one at a time. First, think of what is the ideal bond angle first. Then consider any deviations from it, all right? So let's do that oxygen first. That oxygen has what's attached to it? It has 2 lone pairs and 2 bonds, all right? It just has this bond that has a whole bunch of other crap attached to it, but you can just see, okay, there's 2 bonds, 2 lone pairs. That's all we have to consider. We don't really need to think about what else is it's attached to. All right, so those 2 numbers added together, that gives me an electron domain of 4. All right, and so what shape is 4 electron domains? Tetrahedral. And then I ask myself, what is the ideal bond angle in a tetrahedron? It's 109.5, right? But will this oxygen adopt exactly that ideal bond angle? No. Why? Because there are lone pairs. There's lone pairs present. So what is it going to do to this bond? Is it going to open it up or kind of bring it closer together? It's going to bring it closer together because lone pairs, they're big, fat, and juicy, and they just push everything closer together. So I'm not going to give an actual exact number. I'm just going to say, oh, this bond angle is going to be much less than 109.5 because there's 2 lone pairs present. All right, so maybe a number could be like 105 or 106. That's probably what you would see. 106, much less. All right, not as much as, or it's going to be come together more than like a central atom that has only 1 lone pair on it, for example. Okay, so let's do the same thing for this carbon atom. So how many electron domains? 3. Cool. Are there any lone pairs to consider? Nope. So what shape is that? Trigonal planar. And so if we draw a trigonal planar, all those ideal bond angles are what? 120 degrees. Okay, so does that central atom have anything that will make it deviate from 120? That double bond, yeah. Double bonds, what? Do they take up more or less room than a single bond? More. So I like to just draw it like that and think, okay, that bond is going to take up more space. So what is that going to do to this second bond angle, this indicated bond angle right there? Is it going to make it smaller or open it up? Where I've placed that bond angle. It's going to open it up, yeah, because it's adjacent. It's not opposite of that double bond. It's actually next to it. So we're going to open up this bond. So we're going to actually see a bond angle that's slightly more than 100 degrees, or 120 degrees, right? If I indicated this bond angle would be less than 120 degrees, but I didn't indicate that on this molecule. I wanted this bond angle. So it's going to be slightly more than 120 degrees because it's right next to that double bond, and it just opens it up a little bit more. All right, and then finally, this third bond angle, what's that going to be? What's that going to be? So we do the same exact idea. This has 3 electron domains, and it has a double bond present. So are we going to open up this bond angle or close it down? We're going to open it up again, yeah. So again, this bond angle is going to be slightly more than 100 degrees, 120 degrees. All right. Again, so if I said this bond angle right here, if I called this bond angle number 4, what would bond angle number 4 be? It would be exactly 120, more, less than 120. This one's going to be less than 120, yep, because it's opposite of where that double bond is, okay? So all of this is contingent on, do you know your electron domain shapes? And then finally, if you know those bond angles, just understand that lone pairs and double bonds, they just take up more room and will slightly deviate those ideal bond angles. All right, so those are our bond angles, okay. So let's go into a little bit more detail of 5 and 6 electron domains, because I already introduced the idea that lone pairs take up more room. than single bonds. And that becomes important in shapes like 5 electron domains, trigonal bipyramid, and it becomes important in octahedron molecules, because where we place the lone pair, once we consider lone pairs on this molecular or electron domain geometry, it becomes important. So let's look at 5 electron domains first. So 5 electron domains, we call this trigonal bipyramid. And the reason we call it this is that you can, if you look closely, you can see a trigonal planar shape right here. So these 3 bonds make up a trigonal planar shape. If you look down the center of this molecule, see, you can see the 120 degrees trigonal planar. But in addition, on a trigonal bipyramid, we kind of have this north top part and this bottom part. All right? And so this is a trigonal bipyramid where we have this top part and lower part, and we call the top and lower part the axial positions, versus where we call the trigonal planar part, we call this the equatorial position. I like to think of it, the equatorial position is like the belt of the molecule, all right? And then the axial positions are the top and the bottom, all right? And so what's special about a trigonal bipyramid is that these positions, they are not identical. Because if we look at this white atom and we look at the other atoms that are near it, this white atom is 90 degrees from all the other atoms near it. Versus if we look at the red atom here, right, this red atom actually has 4 adjacent other bonds, but the bond angles, we have 2 90 degrees, but then we have 2 120 degrees as well. So we see that the axial position is not the same spatially as the equatorial position. And that is important because if we start with an electron domain shape of a trigonal bipyramid, where we place our lone pair is very important. So what did I say? Lone pair is what they take up more or less room than a single bond. More. So if you are a fat, juicy lone pair, where will you prefer to go? In an axial position or an equatorial position? Remember, you're fat and juicy and you want a lot of room for yourself. Where are you gonna go? You're gonna go in the equatorial position. Because if you live right here, you are 120 degrees away from anything else. Versus if you go in the top position up here, you gave yourself less room. You gave yourself less room, and so you are only 90 degrees away from other things. So you want, if you're a fat, juicy lone pair, you want to go right there. All right, so that's what we see here in terms of our shapes. This is our parent geometry with 0 lone pairs, is a trigonal bipyramid, but once we put 1 lone pair on, see how it goes into the equatorial position? All right, in our equatorial position? All right, so that's if we have 1 lone pair on a trigonal bipyramid. What if we put a second lone pair on a trigonal bipyramid? You ask yourself the same question. If that added lone pair, we want to put it in a place where we give it as much room as possible. Where is it going to go? It's going to go into the equatorial position again. All right, and that's what we see here, where there's 2 lone pairs. See how both of them are in the equatorial position? Because putting it here gives it as much room as possible. All right, and so if you kind of cover up these 2 lone pairs, we see what shape is that? What's the molecular geometry? T-shaped, yep. And so if we have this shape and we want to put another lone pair on it, where is that lone pair going to go? Is it going to go in the top, bottom, or on the side? It's going to go on the side, and will give it the most room, and that's what we see, that we preferentially put lone pairs in the equatorial positions first because it gives that molecule the most room possible, all right? And so that's what we see here. And again, all of them have the same electron domain geometry, but once we have differing amounts of lone pairs, we see that the molecular geometry changes. So here with 1 lone pair, we have a seesaw. If we have 2 lone pairs, we cover that up and we see, oh, that's a T-shape. If we have 3 lone pairs, and this is kind of weird, 3 lone pairs, cover those up, you see that what's left over is linear, all right? Okay, so that is our trigonal bipyramid. There are different spatial requirements. We have our equatorial positions, that's the belt region, and then the top and bottom, which are 180 degrees from one another, that's our axial positions. Okay, so let's do octahedrals as well. So let's place electrons or lone pairs on an octahedron. So if we look at an octahedron, all of the bonds, they're actually identical because they're all they're all 90 degrees from one another. So there's no axial and equatorial positions on an octahedron. They're all identical. So if we start with 0 lone pairs, we have our octahedron. So if we place one lone pair on this molecule, it doesn't really matter where we put it. So in this example, we just put the first lone pair on the bottom. All right, bottom of that molecule. So that's what this first shape is, electron domain of 6, so octahedron, but one lone pair, we're just going to put it right there, right? And so if we cover up that lone pair, what shape is left over? We have a pyramid, but it has a square base. See how it has a square base? So we call this square pyramidal, all right? Okay, so let's pretend we want to put a second lone pair on this shape. So we already have one. So remember, lone pairs, they take up a lot of room, right? Electrons, they want to get as far away from one another as possible. So right now we have a lone pair in the basement of our molecule. So if we want to put a second lone pair on, where is it going to go? Where it gets as far away from this other lone pair as possible. Where's it going to go? Is it going to go here? No. If we already have a lone pair in the basement, that next lone pair is going to go into the penthouse, right? So that's what we see here, the second lone pair. Once we already have a lone pair on there, then where the next lone pair goes matters. And so in this case, it's going to get as far away from the other one, and so it's going to go upstairs. And so then if we look at the shape that's left over, right, cover up those two lone pairs, what shape is that? It's a square. And it's not a pyramid, so it's planar. So square planar, that's what that shape is called, where we have two lone pairs on an octahedron electron geometry. All right, so once we have square planar, and let's pretend we want to put a third lone pair on this. Does it matter where it goes? No, now it doesn't matter because all the 4 leftover positions, they're identical again. So we see, okay, let's just choose, okay, we're going to choose this one back here. So we're going to put the lone pair right here because all 4 positions are the same. And we see that this is the shape that's left over. And so if we just look at the bonds themselves, we can say, okay, what shape is left over? T-shaped, yes. And so this is interesting. There are 2 ways to get a T-shaped, either from 5 electron domains or 6 electron domains, but different number of lone pairs there. So we see that that's T-shaped. Okay, let's pretend we want to put a 4th lone pair on. Is there a preference of where you go? Do you want to go here in these spots? No, if you go in these spots, you're like right next door to 3 other lone pairs. So instead, that 4th lone pair is going to go right here, where it's only directly next to 2 lone pairs. So that next lone pair is going to go right there. And that's what we see over here, where 4 lone pairs, they're 1, 2, 3, 4, they're all within the same plane of one another. And if we then look at what bonds are left over, what shape is that? Linear. And so the idea here is with these kind of more complex electron domain shapes, trigonal bipyramid and octahedron, there's a little bit more complexity in terms of where do we put the electrons or the lone pairs. Again, lone pairs, they take up more room than single bonds, so we want to put them in a position that reduces repulsions of other lone pairs. And so where we place additional lone pairs matter for an octahedron and a trigonal bipyramid, but they don't matter as much for our other shapes because they're just not as complex. All right. Okay, so that's how we got all of those shapes. So in terms of like memorizing these tables, all right, so those shapes that we just went over, they're the same shapes. So here you can see, oh, there's our octahedron, there's our square pyramid, square planar, T-shaped, linear. This describes where those lone pairs go. So you see the first one for octahedron goes there. Next, the 2, they're across from one another. Then once we have 3, they're like this. And then once we have 4, they're all in the same plane. So it describes where those lone pairs go. And so that's how we get these different shapes. Same thing with trigonal bipyramid. We put our first lone pair in the equatorial region. The second one also goes in the equatorial region. And then the third one, all three of them go in the equatorial region because that is the most space and in terms of minimizing repulsions of our lone pair electrons. Okay, so that explains this entire table. Let me ask you a question in terms of bond angles. Let's see here. So I told you in a perfect octahedron, what are the ideal bond angles? 90, yes, 90 degrees. Okay, but what happens when we put a lone pair? Do you think all these bond angles are 90 degrees? No, they're not. Yeah, so these bond angles are going to be slightly less than 90 degrees. All right, once we put one lone pair on. How about when we put two lone pairs on? Do you think these bond angles, what do we think those bond angles are? What do we think? Are they going to deviate away from 90 degrees, or are they going to be exactly 90 degrees? And so look at the symmetry of this molecule. This lone pair pushes the bonds closer together, right? But wait, there's another lone pair that, doesn't it equally push the bond angles in the opposite direction to undo it? So in this example, we're actually going to see bond angles that are exactly 90 degrees because those two lone pairs cancel each other out in terms of deviations. All right, what about this shape? Are we going to deviate away from 90 degrees? Yes, we will. But what about this shape? Are we going to deviate away from 120 degrees or 180 degrees? No, because those lone pairs cancel each other out, okay? And so the idea of the symmetry in this molecule, we're actually, what you don't notice is we're actually applying the idea of vectors. When we see, when we have two lone pairs across from one another, their vectors actually cancel out. And so that's why we don't see a net change or deviations of our bond angles. And that brings us to the next section of these slides where we talk about molecule polarity. All right. So before we move on, here are all the different shapes. Okay. So you do need to know all of these. You need to know their names, how to make them, and their bond angles, their ideal bond angles, and then depending on if you have lone pairs or double bonds present, slight deviations from the ideal bond angles. So you do need to know all of these. And then together with these shapes, we're also going to apply the idea of molecule polarity. So we're going to be thinking about vectors, but we're not going to actually do any math. We're just going to think, okay, do these bond dipoles cancel or not within a molecule, and it will determine whether a molecule is overall polar or not polar. And so that is the next slide. Okay, so we got like 13 minutes, and then, all right. So let's, because now we understand molecule shapes, okay? We understand how we draw the Lewis structures. Doesn't necessarily mean that molecules look this way. So we have to apply Vesper theory. Think, okay, electron domains, they repel one another, they spread each other out. And so now we need to bring back the idea of bond dipoles. You remember those? Bond dipoles, all right, where we look at the periodic table. We look, okay, if the elements are far apart from one another on a periodic table, if we think about the difference in electronegativity of those two atoms, the bigger the difference, the electronegativity, the more polar that bond. So now we're going to bring back that idea of differences in electronegativity, polar bonds versus nonpolar bonds, but now we're actually going to put them on the molecule themselves. Because we mentioned, polar bonds create bond dipoles. Dipoles are vectors. Vectors, you can add them up in three-dimensional space, all right? And so depending if bond dipoles add up or cancel each other out, gives us either polar molecules or nonpolar molecules. So the idea here is we want to think about these bond dipoles as vectors, but we have to think about the molecule's shape as well. So the strategy for determining whether a molecule is polar or not, first you want to draw the Lewis structure, then you need to determine the shape, then you need to identify polar bonds, All right, so basically polar bonds are going to be any central atom that's attached to anything else like other than hydrogen. All right, so we just want to compare those bonds. And then we need to think about, okay, do those bonds, those bond dipoles cancel out in 3 dimensions or not? Essentially treat them as vectors, all right? And so to me, I don't teach math. I can't teach vectors very well because that's a lot of like sines and cosines and stuff, but I'm gonna make it easier for you. I use a strategy called babies versus bodybuilders, and I just think about, okay, if I have 2 babies and they're like fighting over a toy and they're 180 degrees from one another, all right? So you got like a toy, one baby's right here pulling on the toy, the other baby's over here 180 degrees on the toy, and they both pull at the same time. Does that toy move at all if they're 180 degrees from one another? No, because their vectors cancel out. What if it's the same toy, but you have a baby on one side and a bodybuilder on the other side, and they pull on the toy at the same time? Is that toy gonna move? Yes. Did the vectors cancel? No. So that would be a polar molecule. So that's the big idea. Think of bonds, these bond dipoles pulling on the molecule in certain degrees from one another, and based upon what that molecular geometry is, will change whether those bond dipoles cancel or not. So let's look at 2 examples, CO2 and water. Right? So if we look at CO2 and water, so if you look at a carbon-oxygen bond, here are its 2 electronegativities, all right? So carbon has an electronegativity of 2.5, oxygen 3.5. Is this a polar bond, CO? Is CO a polar bond? Yes, it is, yes. What about in water? Water has oxygen and hydrogen. Is this a polar bond? Yes, so both CO2 and H2O, both of them have polar bonds because they have relatively large delta ENs between their central atoms and the atoms it's attached to, okay? But now, that's not the question here. The overall question is, okay, which molecule is overall polar or not? Okay, both of them contain polar bonds, but now we want to consider how are those bonds actually arranged. In CO2, if we like drew a CO2, right, it looks like that. CO2 has how many electron domains? 2, 0 lone pairs, so that would be a linear molecule. A linear molecule is 180 degrees from one another, all right? So this is an example where carbon is like the toy. We have 2 bodybuilders 180 degrees from one another. They both pull on the toy, or they both pull on that central atom at the same time. Does that central atom move at all? No, because those 2 bodybuilders, they cancel each other out because they're 180 degrees from one another. Versus, let's look at water. Water, we already said, has 2 lone pairs, 2 bonds, so it's bent, all right? So now the 2 bodybuilders, they're not 180 degrees from one another. They're about 109 degrees from one another. So in this example, the 2 bodybuilders are on the same side of the molecule. So if they pull on the molecule, is it gonna move? Yes, it will, because their vectors do not cancel. So that's why water is polar, because those bond angles are 109 degrees from one another, versus in CO2, they're 180, so they cancel. So which of these molecules is polar? Water. Water is polar. CO2 is nonpolar because of how the bonds are arranged. They're at 180 degrees, so their vectors, their bond dipoles, or dipole moments, cancel out in 3 dimensions. So I like to think of bonds as, yes, babies and bodybuilders, all right? So let's look at some examples and see, okay, are these molecules polar or not? All we're doing is thinking, do the vectors cancel or not? We're not looking at the extent of like how much is left over. We just want to know, is it nonpolar or is it polar? So do the vectors cancel or not? So let's look at some molecules, all right? So let's look at CO2. We already did this one, but the big idea is here. Here's our central molecule. The 2 atoms that are pulling on that central atom are 180 degrees from one another. So this molecule is going to be overall what? Polar or nonpolar? Do their vectors cancel? Think of those atoms as 2 babies pulling on a toy 180 degrees. Is it going to be polar or nonpolar? It's going to be nonpolar, yes, because the 2 vectors, they cancel each other out, all right? Okay, what about BF3? So we have three fluorines all pooling on that central boron at the same time. Do they cancel? Do those vectors cancel or not? Yes, they cancel. So the molecule is going to be overall what? Nonpolar again. Let me go back to the CO2 example. What if it wasn't CO2? What if it was a carbon and an oxygen and a carbon and a sulfur? Is that a polar molecule or a nonpolar molecule? So yes, the bond angles are 180 degrees from one another, but are the strengths of the electronegativities of the oxygen and sulfur the same? No, they're not. So will their vectors cancel? No, they won't. So this molecule, SCO, is actually overall polar because we lost that symmetry that CO2 had. Okay, so that's nonpolar, that one's nonpolar. Okay, what about NO2 minus? All right, we got two bonds, but now we have a lone pair. All right, so a lone pair has a ton of electronegativity attached to it. So you can think of these two bonds as babies, and then we got a bodybuilder 120 degrees away from it. If all of them pull on that central atom at the same time, what's going to happen? Does that central atom move or not? So you got a bodybuilder over here and two babies over there. Is it going to, or do their vectors cancel or not? They do not cancel. So this molecule is what? Is it polar or nonpolar? This would be polar, yes, because that lone pair screws up everything. You added a bodybuilder to a kid's party. All right, next one. A tetrahedron, CH4. So we got four babies. They're all 109.5 degrees away from one another. Do their vectors cancel? Yes, they do. So this molecule is nonpolar. What if we throw a lone pair into the mix? All right, that lone pair, it just has a different electronegativity. I don't care what it is. All right, it's just different. So now we have three babies and a bodybuilder. This molecule is going to be overall what? Polar or nonpolar? This one's polar. Okay, what about bent, the water? It's going to be polar because we have two bodybuilders and two babies on the other side. And obviously the bodybuilders win, okay, when they're 109.5 degrees away from one another. So you got to think of what the shape is. All right, so that one's polar. Okay, let's move on to trigonal bipyramid. This molecule, 5 babies. 3 of the babies are 120 degrees, and then 2 other babies are 180 degrees from one another. What happens? Is it polar or nonpolar? Nonpolar, yes. You can think of these 2 babies are canceling each other. These 3 babies are canceling each other. All right, and this only works if all 5 of the bonds are the exact same. Okay, what if we throw a lone pair into the mix? Now it becomes polar, yes. What about 2 lone pairs? Also polar, yes. And then students often go, oh, if there's lone pairs, it's always polar. That's not true. Let's look at the next one. Let's look at the next one. Okay, so we got 3 bodybuilders, all 120 degrees from one another. And then we have 2 babies across from one another. If they're all fighting for the toy, does that central atom move? No, it doesn't, because these 3 lone pairs, they cancel one another in the equatorial region, and then the top and bottom cancel each other in the axial position. So this molecule is actually nonpolar. All right, so just because there's lone pairs doesn't mean it's always polar. So you got to think of the vectors. All right, but again, we're just determining, do they cancel or not? Okay, so let's keep going. Let's do 6 electron domains. Octahedral, polar or nonpolar? So no lone pairs. This is nonpolar, they all cancel. Throw a lone pair in the mix, it becomes polar. So now let's throw another lone pair into the mix, but remember, for octahedrons, once you place one, the second one has to go here. So what is this, polar or nonpolar? This one's nonpolar, yes, nonpolar. Oh, that's it. Is that it? Yes, that's it. Okay, so let's, yeah, we can finish these slides. Okay, so let's think about carbon. Carbon always forms 4 bonds. The most typical carbon you'll think about in like organic chemistry is the tetrahedron. So carbon with 4 single bonds into it. Carbon, though, it forms a tetrahedron, but we don't have to make all of the bonds the exact same, right? So the idea here is that carbon, CH4, methane, carbon with 4 things attached to it, it's not flat. Even though, like we draw the Lewis structure flat, CH4 is not flat, that it's a tetrahedron. All the bond angles are 109.5 degrees away from one another. So let's look at these different carbon-containing compounds and determine, are they polar or not? Just think babies and bodybuilders, okay? We don't have to get fancy with vectors. We just need to see, do their vectors cancel or not? So here we have a carbon with 4 identical hydrogens. Is this polar or nonpolar? Nonpolar, because all of those hydrogens are identical. They are all 109.5 degrees away from one another. But what if we throw a fluorine into the mix? Once we throw a fluorine into the mix, this bond dipole, the one with carbon and fluorine, is no longer the same as carbon and hydrogen. These ones are smaller. So again, think babies and bodybuilders. Do their vectors cancel? No, they don't. So this molecule is actually polar, yes, once we put a fluorine in it, okay? What if we have 2 fluorines? So these 2 vectors are a lot larger than these 2. Polar or nonpolar? Also polar. And this one's tricky because if you think carbon is, CH4 is flat, so let's pretend you think that this molecule is flat, and you draw it like that. If you think carbon is flat and you look at that, and if you do babies and bodybuilders and think carbon is flat, what does this molecule look like? Does it look like it's polar? No, it looks like it's nonpolar, right? Because I put the 2 fluorines across from one another. But you have to remember that carbon is not flat. Just because I draw it like this doesn't mean that it's flat. I actually gave this question I teach chemistry for engineers, and I drew exactly this. I drew this, and then I think I drew this. And I said, like, which of these molecules are polar? Like A, B, both, or neither? Which ones are polar? And so in this example, this is actually the same molecule, just drawn the same. Like, I just drew it a little bit differently, but it's the exact same molecule, right? Where we have 2 fluorines, but one, it looks like the fluorines cancel their vectors out, but carbon is not flat. It's actually a tetrahedron. So both of these molecules are actually the exact same. They're the exact same. They actually look like this. Both of these molecules are polar. This question did very, very poorly on the exam. A lot of students said that this molecule was nonpolar and this one was polar, but in actuality, both of them are polar. They're actually the same molecule, right? Because carbon is not flat. Just because I drew it that way doesn't mean it's flat. Okay, all right, that's 2 fluorines. What about 3 fluorines? Polar or nonpolar? Polar, yes. Then what if we go to 4 fluorines? Now it's nonpolar because now we have 4 bodybuilders all around it. Yes. Give me 1 more minute. Yes. Yes. And now let's do 1 more. Okay. So yes, do not think CH4 is flat. It's actually tetrahedron. So we're going to do 1 more. These pictures. Which ones are polar or not? So this one's a little bit trickier. These molecules are flat. All right. These are flat. So what we're comparing is, okay, where are these carbon-chlorine bonds? All right, so these carbon-chlorine bonds are making a very, very strong bond dipole. So this molecule that I just drew on, would you think this is polar or nonpolar? Polar, yeah, because chlorines are really electronegative. It's pulling on that molecule in one direction. What about this molecule? So note where the chlorines are. Now they're on this side, so they kind of go this way. Do you think this molecule is polar or nonpolar? Also polar, yes, great. And now let's look at the last arrangement. These chlorines are oriented this way from one another. What do we think that molecule is? This one is nonpolar because their vectors do cancel. All right. Okay. So that's bond polarity. Cool. We have 6 minutes left. So I'll end with the demo that I promised you.